the reason I'm doing this research and talking to you today is because I really believe we should come back to the old dream of the 80s of using machine learning for building intelligent machines and possibly even understanding how brains manage to do the feats they do. So I will start by telling you about representation learning. Deep learning is a particular case of representation learning, something that has always been important for machine learning, I think, but has been neglected until the last few years, to think about not just how to handcraft representations, but also to have the machine discover representations. And then I'll go through specific algorithms that some of which date from the 80s, and some have been very successful recently, like convolutional nets for images, and others are more modern and help us to learn representations in an unsupervised setting. Then I'll go through practical considerations and a few words about applications and challenges. So this is the program for the 3 lectures I'm giving, 2 today and 1 tomorrow. How do we get AI? How do we get machines to be smart? Well, one thing that dawned on me a long time ago is that what AI means is to have machines that understand the world around us. That's really what it means. And the world around us is complicated. It would require a lot of knowledge to reach the level of understanding of the world around us that we have, and that's what we would call AI. So if there's any hope of building an intelligent machine, this machine is going to have a lot of knowledge in it. A lot more than we currently put in our machine learning systems. So the models we currently train are way too small in terms of the number of degrees of freedom they have. It also means that the number of examples we're using is probably not enough. Although we may also not be very efficient statistically in the way we use data. So of course we'll need learning. And for me, learning means essentially 2 things. On one hand, priors, so a little bit of knowledge you put in, and optimization and search, which are really challenging, and these 2 things have to be put together. Sorry. You need to think about also the generalization aspect. I'm sure Neil has explained these notions to you, and I'm sure you already know these notions from what I've seen at the posters yesterday. But today I'll be trying to convey a view of generalization from a geometric and probabilistic point of view, as the question of guessing where, that's the geometry part, where probability mass should be put. Right? That's how I think about generalization. And once you start thinking about it that way, you realize that in the kinds of tasks we want to solve with AI, where there are lots and lots of variables, the number of configurations of values of these variables is huge. And that's essentially what makes machine learning hard and connected to this notion of cursive dimensionality. One idea behind a lot of what I'll be talking about today and the deep learning in general, I think, is how do we learn good representations in order to fight this cursive dimensionality, to get around this apparently intractable problem of guessing properly where to put probability mass. And I believe that one way to think about how to solve this problem is this kind of dream of a machine that discovers the underlying factors that explain the variations in the data and separates them, disentangles them. If only a fraction of that was possible, it would make it would eliminate the cursive dimensionality. It would make life of the learner much easier. So it's more of an objective, but you can think about it as essentially making sense of the data, finding explanations for it. All right. So let's, now that I've explained the whole of my presentation in one slide, I'll go a bit slower, and then I'll go even more slower later. So I started by talking about the notion of representation. So typically representation would be how we take the raw data and transform it as input to a classifier trained by some machine learning algorithm. And that representation would be handcrafted. It would depend on our knowledge of the field to figure out what sets of numbers we could extract from the raw data that we think might be useful for the learner. And we would like to make these features typically sensitive to the factors we think matter and invariant or insensitive to the factors we think don't matter for our task. And this takes a lot of work. I would say that in industrial applications of machine learning, this is typically what is being done 90% of the time. So what we want to do is replace that box by machine learning. So how do we get the machine learning to discover good representations from scratch? Now, of course, if you have some prior knowledge about good features, you should use them, but you can only go so far with handcrafting, and you like the learner to do most of the job. So that's the question we're trying to answer. To get a sense of why this is powerful, I want to mention some work by my brother, Bengio, on the left, top left here. He's with his colleagues at Google behind the system for image search at Google. And I'm sure many of you have already used it that associates images and queries. So you type something and it returns images that are somehow related. And the way it works is it learns from data a representation for images and a representation for keywords. So there are two functions. This doesn't work. There are two functions. One that, I'll just point like this, one that goes from images to this 100-dimensional space, say. I guess nowadays they probably use larger vectors. And one that goes from queries, which are discrete entities that have some time structure, to the same space. And they learn these two functions simultaneously so that, thank you, so that when somebody types dolphin and then clicks on that image, it's going to try to make the two functions, put their output close to each other. All right, and so this idea of learning representations for keywords or words, actually older, is something I did in a NIPS 2000 paper where we used a particular kind of neural net that I'll talk about later to learn representations for words in a much smaller vocabulary than what they're doing at Google. And then you can take these representations, which are vectors of dimensions, say 100 or 200 or something, and do a nonlinear dimensionality reduction so that you can visualize where they stand with respect to each other. And you can't see, but this is a cloud of words. But if we zoom in, we start seeing things, and you probably don't see much yet, but if you zoom in more, you see that words that are semantically close end up close to each other. And it's just the learning which makes this happen, because words that co-occur in similar contexts want to be close to each other, because it's going to make the job of the learner easier, and it also allows it to generalize. This is other clusters where you see verbs, conjugations of the verb to be, and so on. Something really funny happened recently in this field of learning representations for words. So this is fairly recent, about a year old. Tomasz Mikolov and his collaborators, first at Microsoft and then at Google, discovered that these representations for words, they carried some kind of analogical structure. So you can reason by analogy by doing very simple operations on them. So, as I said, each word is mapped to a point in this real valued space, so a vector. And you can take the representation for France and subtract it from the representation from Paris, and you get another vector. And it turns out that this vector is almost the same as the difference between Italy and Rome. And you can guess why, because Italy is to Rome what France is to Paris. And it not only works for these 4 words, but for a whole data set of these analogical pairs. And they tested this on this data set and basically beat the state of the art without any supervised learning. So this comes out without training a learner to answer these queries like, what is Italy is to Rome, what is France to what? And so you get things like king minus queen is close to man minus woman and so on. So that's pretty amazing. It just came out of unsupervised learning. Oh, I forgot to say something important. Please interrupt me any time you want. I would rather, go through less material, but answer your questions along the way. So really feel free to raise your hand and ask any question. All right? Okay, so this was a little introduction to the notion of representation on one hand and the idea that you could learn representations. And I used words as an example. And deep learning is about learning representations with multiple levels, so multiple levels of representation corresponding to multiple levels of abstraction and complexity. So in a typical sort of graphical model way or neural net way, we think of the input X as being our raw representation given by the user. But we're going to learn a representation on top of it, and then we're going to learn a representation on top of this one, and so on and so on. And the higher level representation, which you can think of as composing pieces from the lower level, is going to be more nonlinear, more abstract. So why is that interesting? I will very briefly mention some theory about why having these multiple levels of computation or representation could be advantageous from a machine learning point of view. But the gist is that you can be much more efficient in representing functions if you have such multiple levels of nonlinearity. In fact, you could be exponentially more efficient in some cases, if you're lucky, if your data has such structure. And it's a reasonable prior that in the world around us, there is a hierarchy of concepts and features. That's how we learn about the world. That's how we make sense of the world as scientists as well. There's also motivation coming from looking at how the brain works. In particular, the visual cortex and the auditory cortex, which we understand better, seem to perform computation in this series of stages where at each stage we see more abstract computational features being detected. Later in my lectures, I'll talk about how representing data at a more abstract level helps us with Monte Carlo Markov chains. I'm not sure how much Neil told you about MCMC, but did he mention anything about them? Nothing? All right. Huh? Yes, Ian will talk about it, and hopefully he'll talk more about it than I will, but I will certainly talk a little bit about MCMC, which are methods used in many machine learning algorithms for generating or sampling from a distribution. So I'll get back to this. And then, of course, some of you have maybe heard of deep learning, like in reading the New York Times and stuff like that, because lots of companies are becoming very excited about deep learning and how it could be used to advance approach AI and, in particular, solve tasks in computer vision, speech recognition, language modeling, and so on. So there's a lot of excitement because in the last few years, a lot of breakthroughs happen in terms of benchmarks and applications. So I'll mention very quickly some of these. All right. So this is an illustration coming from a paper by Hong-Lak Lee and collaborators at Stanford with Andrew Ng, illustrating what it could be to have, what it could mean to have multiple levels of representation. Here, what they're trying to illustrate is the notion that one form of hierarchy that seems to be discovered in these models is the parts hierarchy, how parts can combine to form objects. So the figure shows in each little square the kind of input that a particular unit in a deep neural net, deep graphical model likes. So the low level, the layer 1 units like an oriented contrast, also known as an edge detector, typically, or other kinds of simple shapes. And these would actually be localized in the image at a very particular place. And they would be replicated at all positions. If you look at the units higher up in the hierarchy, what they like seems to be parts of faces like nose and eye and so on. And higher up, the units like to see whole faces. So this is one example, but really there's something more generic going on. In fact, every time you write a program, typically you use a deep representation. What I mean is, we don't write program by taking just a sequence of instructions in one big main program. Maybe that's how it used to be done in Fortran in the 50s or 60s. But nowadays we like to write program like this, where some subroutine is going to be reused many times, maybe recursively. And so the whole code is much more modular, much easier to write, much easier to read, to reuse, and so on. But in machine learning, we've been doing things like this. And we need to do things like this. In machine learning, until a few years ago, most supervised learning was based on this kind of structure where you take the input data and you map it to some fixed representation, like a feature vector of a kernel, or a learned representation in the case of a one hidden layer neural net, or of boosted trees or boosted stumps. And then just some kind of linear combination, maybe a logistic regression on top would get us our answer. So this kind of structure, which has been dominant in machine learning for decades, is what I call shallow. It would have usually one or two levels of composition. And that would correspond, in the case of neural nets, with a neural net with one hidden layer or zero hidden layer, like a linear classifier or logistic regression and things like that. So people thought that this was enough for doing the job, because there are these old theorems called universal approximation theorems that tell us that you can represent any functions with two levels where, depending on what you choose for what the middle layer does, but things like logic gates, formal neurons, which just take a binary decision based on an affine transformation, or RBF units, which correspond to what you find in, say, Gaussian kernel machines. These are enough to represent any function you want if you just put enough of these guys, the intermediate units. But these theorems don't tell us how many you will need. It turns out that there are families of functions you can construct for which the number of these intermediate features, intermediate units that are needed to represent those functions is huge, is exponential, say, in the input. even though if you allowed yourself to have more layers, more depth, then you could do it efficiently in polynomial or linear number of computations and units. So that's the gist of these theorems, and one of the motivations for deep learning. So something happened in 2006. Previously, people had tried, and I did in the early 90s, to train deeper neural nets, and somehow we had failed. And not just one person, but a bunch of different labs had the notion that, oh, it would be nice if we could train deeper nets. They should be more powerful. But we had failed. And what happened in 2006, essentially thanks to Jeff Hinton at University of Toronto, is that some unsupervised learning procedures turned out to allow us to train these deep nets, these deep supervised neural nets, much better than was possible before. And that started the field of deep learning, essentially. Since then, we've found other ways to train deep nets that don't even require unsupervised learning. But unsupervised learning, as you'll see, is still very interesting and useful, especially when you have few labeled data or you want to do transfer learning, and remains one of the challenges for future research because we don't know how to exploit unlabeled data nearly as much as we should. So today, I guess today I'll tell you about some of these algorithms that we used in RBMs, which are undirected graphical models, probabilistic models, restricted Boltzmann machines, that's what the acronym stands for, a bunch of autoencoder variants and sparse coding variants already were there in 2006 and used in a scheme in which we call stacking of single layer learner or layer-wise pre-training, in which we take the data, learn a single layer model that results in a new representation of the data. So we have the raw data here, and we learn a probabilistic model that has latent variables here, H1. Once we've done that, we have a new representation of the data, and we can apply the same recipe as if this was, the data, but you just represent it differently, and do it again and again, and get a stack of these representations. And then we could use these as initialization for a deep neural net, either for a supervised or unsupervised job. So the idea was really simple. And it's because training neural nets, and especially deep ones, is non-convex. There's an optimization problem that this initialization trick made the difference. And we found later that we could also get to train deep nets by being careful about how we initialize them without unsupervised pre-training. So other forms of initialization that are simpler, by playing with non-linearities. Rectifiers and max out are sort of the non-linearities that people use these days that are very successful. And new forms of regularization have been discovered in the last few years. One I'll mention called dropout, which is also very successful. As for the unsupervised pre-training strategy, it's still useful when you deal with rare classes, when you want to transfer to new classes, when you have small labeled sets, or simply as a regularizer. So hopefully by the end of these sessions, you will understand better these terms. Any question? Yeah.
So to get these very rich models, you mentioned that the optimization isn't correct.
That's right.
Is it your intuition that however you get a rich model, you're always going to have difficulty in that sense? That there could be no context?
Yes. It is my intuition, but and I've I'm not the only one to have this intuition, and people have been thinking about it and trying to prove it one way or another, but I don't know of any formal result in that direction. Vladimir Vapnik was convinced the answer was no, but it's up in the air. So there's, by the way, there's a trivial sense in which you can get a very complex function with a convex criterion, and we had a paper with my ex-student Nicolas Leroux called infinite neural networks or convex neural networks, and it's related to what you just heard this morning with Gaussian processes and what Radford Neal did in the early 90s. If you take a neural net and you allow its number of hidden units to go to infinity, then you don't need to learn the weights because you have all of them. All of the possible weight vectors are there in that infinite set. And so you just need to learn the output weights. And so that's convex. Right? So we've turned a non-convex problem into a convex one, but that has an infinite number of parameters, which can be reduced, thanks to the kernel trick, into no more parameters than the number of examples, because you can't span more than that anyways. So you'd think that, yes, you can do all these things and staying in the convex world, but there's something you lose when you do that step. You lose the ability to learn a representation. And that comes with, as I'll try to argue, a very powerful, it's a prior that, whatever prior you put in your representation can be wrong, but if it's reasonable, it can bring in a lot of statistical power. And so what you see in practice is these deep neural nets can, if they're trained properly and there's enough data and so on, they can generalize really well. And I'll try to explain the intuitions why I believe this happens. So there's been a lot of stuff going on in the news that has made deep learning very popular. The last bit of news that is not here that happened in the last few months is Google buying a company called DeepMind that's located in London. It's specialized in deep learning and reinforcement learning for a very large sum of money, supposedly $500 million. So it's gotten, many other companies scrambling to suddenly do deep learning. So we have to be a little bit careful of all this buzz. But there's some real science behind, and I'll try to explain what I know about it. One question that I get asked sometimes is, okay, so how many levels before it's deep enough and considered deep? Right? So the answer to this is it's a data-dependent answer. Maybe for your distribution, 2 or 3 levels is enough, given this, the type of parameterization you've chosen. So to be able to deal with the fact that the right number is data-dependent, what we want for deep learning is a learning algorithm that will, gives us a recipe to have as many levels as needed, right? So we don't have like a different algorithm for the first layer, the second layer, and the third layer, and the kth layer. There's no like k different algorithms. There's one algorithm that hopefully works for all levels. And maybe, some people think, okay, so maybe if your input is images, you want to put more prior knowledge about it, and the first level should be, accordingly different. But really, what makes it deep is we have a generic recipe for adding more abstraction on top of abstraction. That's what makes it deep learning, I think. Right, so in the Gödel neural nets, that I will explain because I have a feeling that it's not always taught anymore in machine learning classes throughout universities of the world. It was a standard staple for machine learning in the 90s, but in the 2000s it's kind of got to disappear somehow. And then these events of the last few years, the success of deep learning has brought it back. So let me, please indulge my explanation of very old and simple things. So in a typical feed-forward neural net, you've got an input which you can represent as a vector, and you do some parameterized transformation, like an affine transformation of it, and you apply some nonlinearity, and you do it many times. And at the end, you typically produce a conditional distribution over some target variable, like you predict the probability of some class given the input. And you can think of the intermediate layers as representing different levels of features, different representations. And if you're trying to predict something out of the input, the last layer is really trying to capture a conditional distribution where the parameters of the output distribution are going to be functions of x, and you're going to learn that function. Well, some of the things that have changed in some of the modern deep learning systems is that instead of the arrows going only up, they can also go down. And so now you can do things like generate inputs or fill in missing inputs. And you don't even need an output layer. You might just represent the input distribution somehow. Now, let's go back to sort of machine learning basics, even more basic than neural nets. So what we're really trying to deal with is the curse of dimensionality. What does that mean? So if I have a single random variable and I discretize it into bins, and I want to, learn y given x, or maybe count, estimate p of x, I can just do some counting in each bin to produce my answer. Like how many times y was 1, or how many times did x fall in this bin, and I can answer questions about density, about a prediction of y given x in a very simple way. That's what a histogram does. And if I only have a few number of values of x that I need to distinguish, this is going to work fine, this histogram. And you can make it a bit better by using non-parametric density or non-parametric regression. But what happens if you got two variables? Now you've got, if I have 10 different values for each variable, I've got 100 cells that could, I have to populate with enough data. So okay, so if I have thousands of examples, and I might be fine. If I have 3 variables, now I've got 10 by 10 by 10 cells. It maybe becomes a problem where there'll be lots of cells for which I've seen no example, and still, when I get a question there, I don't know what to do. So I could extrapolate, as you would do with a kernel machine, by looking at neighboring cells. But you can see that this is not going to scale to 1,000 pixels or even 1,000,000 pixels. Right, there are just too many configurations. So to understand better what's going wrong, first let's see what's working. What's working here is that we're able to generalize because we introduce a prior. And the prior we would typically use in these non-parametric systems is smoothness. So I'm trying to learn the function in violet, and my estimator is the dotted thing. And it works because the target function here doesn't have that many ups and downs. And so I don't need that many examples to cover all the ups and downs of the target function. That's why I'm able to simply interpolate, or something a bit smarter than interpolate, but basically interpolate between examples, so neighboring examples, in order to generalize. And I might even be able to extrapolate a little bit. So if I zoom in this thing that I had before, I basically can take two nearby examples, interpolate, and because the function that I'm trying to learn doesn't vary too much, and I have enough examples to cover all these ups and downs, just a simple interpolation will work. And that works because I'm assuming the function is smooth enough compared to the coverage that my examples give me. But in reality, the functions we want to learn are very complicated. I realized this one day when I thought about the manifold of images corresponding to the image of a digit as you rotate or translate it. So if you try thinking about this a little bit, you'll see that if you take your image and you think the manifold of images corresponding to, say, translation, rotation, scaling is very smooth, like in the picture, but it's not. It's not smooth at all. It's highly curved. So as soon as you move by just enough pixels corresponding to the width of the, where the ink is, your manifold is 90 degrees from where it was before. And so it keeps going in other directions and moving at sharp angles. So the manifold is far from smooth, the kinds of manifolds we see in images, for example. And one thing I want to add about the curse of dimensionality is that really it's not about dimensionality. You could have a very high dimension, but if the manifold where the near which the distribution concentrates is very smooth, or if the function I want to capture is very smooth, then even in high dimension, that's not going to be a problem. I can still use my, Gaussian process regression. It's going to work. Where my Gaussian process regression is not going to work is if this function I want to learn has a lot more ups and downs than the number of examples I have. So we actually had a theorem about this a few years ago that suggests that it's not so much the dimensionality than the number of variations. So you could have a one-dimensional function that varies a lot, and it would be very hard to learn. Basically, the theorem says that if you want to represent classify or represent a function that has many ups and downs with a Gaussian kernel machine, you need at least as many examples as the number of ups and downs. And of course, if you have d inputs, you can construct easily a function that has an exponential number of ups and downs, exponential in dimension, like checkerboard, for example. It goes up, down, up, down, up, down. Can go exponential in the number of dimensions. But it's really the number of variations that really kills us. Okay, so I've talked about this notion of manifold. It's one of the assumptions that we make about many of the tasks we care about, that I care about, which I call AI tasks, that the probability mass is concentrated. The right answer, the right model gives almost zero probability to most configurations and a very high probability to a very, very tiny volume of configurations. And you can convince yourself that this is true by thinking about creating images by randomly picking each pixel. What's the probability that you find something that looks like a natural image? Or you know the old thing about the monkey, typing Shakespeare, right? What's the probability that you'll get a nice text out of randomly picking letters? It's, infinitesimally small. That's what I mean by probability is concentrated. So if it's so concentrated, and you can feel that it's really concentrated if you think about these examples, then the real job is to figure what are the places where the probability should be high. And the actual value of the probability isn't that important. So we need to guess where to put structure. So one way to visualize this question is think of the data as telling us that there's a high probability. So this is, say, 2D data, and each point here is an example. So the data tells us that this configuration of x and y is likely because we've seen it in the data. So that's the empirical distribution. And we can use the smoothness assumption to go further and tell us that, well, because we're expecting the function to be learned to be smooth, that means that if the probability or the output we want to predict is high here, then it should be high nearby. And so we can just put little balls around. And that's useful, but it's not enough in high dimension, as we've seen. That's the curse of dimensionality. So we need something else. We need to discover that there is some structure, that, oh, these points actually together, there's a simple equation or a simple structure, statistical structure, that allows me to interpolate or to extrapolate between them. And in 2D, it doesn't look impressive, but if we're in a very high dimensional space, this is a very special place here that I've chosen to put probability mass on. Okay, so there is some hope to generalize non-locally, so beyond the neighborhood of your examples, beyond what traditional non-parametric statistics gives us, but it's going to require some other priors besides smoothness. And the main theme of deep learning is to exploit compositionality, to assume that there is some compositionality in the function we want to learn. And humans do that too. And if there is a good way to describe the world around us with this prior, then we can get a huge advantage, at least in theory, because things that can be represented in a compositional way, can be represented very efficiently that way, but it would be very inefficient, very expensive to represent them otherwise. That's what the theory tells us. Okay. So let's, I'm I've said these things already. Let me go here directly to try to give you an example of compositionality that is at the core of the notion of representation, of learned representation. And it has to do with a very old notion from the 80s, actually coined, I think, by Jeff Hinton, but if not, in those years in the mid-80s. It's the term distributed representation. But before I tell you about the distributed representation, I'm going to tell you what is not a distributed representation. So clustering and nearest neighbors and Gaussian kernel SVMs or Gaussian processes, many local non-parametric density estimation, decision trees, all these things don't take advantage of a distributed representation. Instead, what they do is they take the input space and they break it down in regions. And depending of the algorithm, they do it in different ways. But typically, they break it in such a way that we'll have at least one example in each region. In the case of clustering, there will be enough example in each region. And those regions don't have to be hard, like in this picture of, I guess this is like a nearest neighbor classifier. There could be soft regions like in kernel density estimation and so on. So now for each of those regions, I could have a different kind of answer. For example, I could ask what's density, which would be basically related to the volume and the number of examples falling in there. And I could do a regression and ask, what are the values of the y's for those that are inside this region. And I could interpolate between neighboring region in the usual way, as I was telling you before. So that's very powerful because I could represent any function. You can immediately see how I can represent any function so long as I can break down the input space in enough regions. And for this, I need enough examples to essentially cover the ups and downs. For each up and each down, I need a different region. And that's going to work. It's very powerful. But how many regions am I going to be able to distinguish with this? Well, roughly about the same number or no more than the number of examples, or if you want the number of parameters. You can think of it like maybe a region is defined by the center of it and some value we want to output there. And so these parameters that define the region, or the examples that allow you to estimate those parameters, we can count how many are needed compared to the number of regions, which tells me how rich is the family of function I can represent. So here it's simple. There's a linear relationship between the two, the number of regions and the number of parameters or examples. Now, in a distributed representation, things are a bit different. We're also going to get regions, but the way we're going to get them is we're going to define some features. So this is going to be our representation. And these features are going to be non-mutually exclusive. In other words, think of them as, say, bits, and any one of them can be 1 or 0, and most of the configurations are legal. So now the number of bit configurations here is exponential in the number of these bits. Of course, it's 2 to the number of bits. And each of these bit configurations, or almost all of them, will correspond to a region in input space. So how do we get these regions? So for example, here in the simple neural net or RBM, each of those bits correspond to being on the left or right of a hyperplane. So each of these is defined by a weight vector, which correspond to the normal of a hyperplane. And so each of these you can think of like a little neuron that turns on when you're on one side and off when you're on the other side. And now the regions correspond to all the possible configurations, meaning, I'm the left on that one, the right of that one, and so on. So that gives us the sets of ones and zeros. Well, now let's do again our counting game. How many regions versus how many examples do I need, or how many parameters? And now you see you're going to get exponentially more regions for the same number of parameters or examples. And why is that? Because to learn about one of those features, I need just enough examples to define this hyperplane. And I don't need to see examples in each of the possible configurations in order to say something meaningful about those configurations corresponding to those regions. Now, you can say, well, what's the catch? I mean, I have an exponentially more powerful thing, and I must have to pay a price for this. And indeed, the price is that you're assuming something about the structure of those regions. You can't anymore, like in the previous picture, I could have any pattern of regions, any configurations of regions. Here, I can't. It has to be that those regions correspond to these intersections of a half plane. So this is a very tight constraint. We can relax that constraint by making, instead of these being hyperplanes, I could make them being complicated nonlinear shapes. And this is actually what we get with deeper networks. But the gist here is there's still going to be a prior that somehow these features are meaningful by themselves. That when I have a new configuration, it makes sense. So let me give you an example. Let's say that this says whether this is the input is an image, and this guy tells me whether it's it's an image of a person, and this guy tells me whether it's a male or a female, a child or an adult, and this one tells me whether he has glasses or not. So you can learn about glasses, you can learn about height, you can learn about age, you can learn about gender, almost kind of independently. And now, even though you haven't seen all of the configurations of these attributes, you can generalize to new configurations. So that's the assumption, that there exists these factors that can be composed together in new ways, in a way that's meaningful and allows you to generalize. Right. So the other reason why deep learning is interesting is that it brings ability to do unsupervised learning to neural nets, which was not as much developed, let's say, before 2006. Of course, there were algorithms before. But these ones have been fairly successful. And why is this interesting? Well, most of the data that we can put our hands on is unlabeled, and so that, another argument is that most of the signals we're getting from our perception doesn't come with a label, and the brain has so many degrees of freedom to set that the few labels we're getting are just not enough. We would be overfitting if we didn't do unsupervised learning as well as some kind of supervised or reinforcement learning. Practically, in applications, the unsupervised learning can be very important for doing what I call transfer learning. This is what allows humans to generalize from very few examples. If you compare current state-of-the-art machine learning with how humans learn, there's one thing that's striking. Humans can learn a new task, like recognizing a new category of objects, with just one example, or two or three, or just very few. The current state-of-the-art in computer vision requires thousands of examples of a new category. So we are far from that. But how do humans do it? They do it by exploiting previously learned representations, by doing some kind of transfer between what's been learned and the new data, the new distribution, the new classes. So what is it that allows us to transfer from, say, unlabeled data or things we've seen before to new examples of a random variable y that we want to predict given x? It's a prior about the relationship between p of x and p of y given x. Let me show you a picture. So that's the standard thing that is used in machine learning to explain semi-supervised learning. If I'm just doing purely supervised classification and have two examples, one of the green class and one of the blue class, I'll probably want to put a classifier like this. But if I have unlabeled examples, then you would agree with me that this would be better. But that means I need to do what's called semi-supervised learning. I need to learn something about the distribution of the x's and hope, by making a bet that this prior is good, that the structure of p of x, which is aligned in this direction, reveals something about the structure of p of y given x. And here they're perfectly aligned. And there's a good reason. I mean, it makes sense here because the two categories here correspond to two manifolds. And those manifolds, what you really want to do, what we're saying here is that these manifolds correspond to categories, that a category corresponds to a set of points that's quite disjoint from the set of points corresponding to another category. And so moving along the manifold of one category, you don't change the category. That means that the linear classifier has a normal that should be orthogonal to the manifold. And that's why we get this. So here's a slightly more complicated example that's, textbook example of semi-supervised learning where we have the green points and the violet points, but only the circles are labeled. So the few, like the single green circle here allows me to tell, if I do capture the input distribution of the greens here, that the classifier shouldn't be this straight line here, but should be this curved line, which should be doing a much better job at classification. But you need some, assume something about the data for that to work. Let me skip a few things. Right, so another form of composition, so we've talked about having multiple factors in a distributed representation. There's another form of composition, which is when you take these factors and you compose them by stacking them on top of each other, by defining one thing as a function of other things. So a very, very simple illustration of this is seen in the theory of sum product networks. So a sum product network is a circuit where each node computes either a multiplication or an addition. And you've got input nodes and output nodes, and you're basically just computing a big polynomial. But instead of computing it as just a big sum of products, which we know can compute any polynomial, which would be a circuit with 2 layers, you could do it with a deeper circuit, and that may be advantageous. And in fact, we can prove that there exist families of polynomials for which it would be exponentially advantageous, exponential in the depth here, to have a deeper circuit. And why this works is you can see illustrated here. Consider this product x2 times x3. It gets reused here twice, so it's part of this polynomial, which corresponds to the computation of that node, and that one. So if we were to compute these two directly and separately, we would redo the multiplication of x2 and x3 twice. But if we go higher up, now x2, x3 comes 4 times, and if we keep going up, the number of times it could show up is exponential in the difference in depth. So because of the reuse, and you can have pieces of the network that are going to be used in exponentially many places if you consider higher up units. And so you can exploit this to show that you can represent some polynomials, basically polynomials that in a sense factorize in a this graph is really a way to factorize in a complicated way a polynomial. And those polynomials that factorize like this, they would be very expensive if you would just flatten them into a sum of product. Just like we are seeing here, higher up node, they have lots of terms. So if we flatten this, we have lots of terms, even though the number of computations to get there may be much smaller because some things have been reused. Yes?
But how do you recognize a situation in which you had a multi-level situation from one in which you had a multi-scale situation in which is a low-level composition but on a different scale that can be interpreted as maybe a combination of low-level combinations when actually
I don't have a recipe for answering your question. I think it's a different kind of composition when you introduce multiple scales. And for some types of data, it's clearly important. We've seen it important in images, in music. It's clearly important in text as well, although we're not currently exploiting it. Learning multi-scale, deep architectures is something many people want to do, and there are a few papers, but it's clearly underdeveloped. So actually, this is roughly related to what I was talking about here in the next slide. Something that was said against neural nets in the 80s and 90s is that they could only learn these very simple functions. And they didn't have the kind of recursion that we see in human thought and human language. But actually, that's easy to fix. If you take the same component, like this pink box, and you reuse it many times over time, you can essentially compute any function in a recursive way. And you can also reuse the pink box in a different way, like this. So for example, this has been proposed by Léon Boutou and has been developed by Richard Socher with great success in a number of applications in language modeling. You think of this, say, the input being a sentence, and what you're doing here is you're combining representations for words into representations for phrases, and the representation for phrases into representations for sentences and paragraphs and so on, just related to your question. And people are trying to find ways, well, how do you find the structure of these graphs which correspond to a kind of parsing decision? And there are some answers, but clearly more work is needed. But the important point is that the same computation gets reused. So suddenly that allows you to deal with variable size inputs or variable kind of structures like trees and graphs. So the key is recursion. So if you can reuse the same piece of computation or parameters, you can introduce recursion in these systems. Another characteristic of these deep nets is that they naturally give rise to multitask learning. So if I have some model of the joint distribution between inputs or the conditional distribution between inputs and targets for a particular task, I could have a separate model for each task, or I could put all my tasks on, in the same big model like this, where maybe the first few levels would be shared, because somehow, let's say the input is an image, and whatever the type of image, you have to do basic things to the image to figure out, what are the parts and the edges and so on that may be shared across different tasks. So the idea is that we're making an assumption, say that at this layer, we're extracting a number of explanations or factors for the raw input, and a subset of them is relevant to the first task, and another subset may be relevant to the second task, and so on. And so we need maybe a task-specific computation here. But we can share all of this, and we gain statistical strength thanks to this. So this is very, very useful when some of the tasks have very few examples, very little data, because they can take advantage of all the work that has been done by training on the other task. And this is a way to get transfer learning that really works well. So in this example, all of the tasks share the same kind of input. But sometimes things are more complicated. So let me tell you about an example that moves a little bit out of the normal framework of machine learning. So in standard machine learning, we think of the data as living in some big table where each row is an example and each column corresponds to an attribute, and maybe one of them is the thing you want to predict. But sometimes, like in relational databases, we have not just one table, we have a bunch of tables. So we could do a cross product of all the tables into one huge table that we don't even want to represent explicitly. And that's typically how we normally do things in machine learning. But there's another way of doing it, thanks to the notion of representation that can be shared across tasks. So here's a little toy example. Let's say I have a table that has a column for person, URL, and event, and another table that has attributes for URL, words, and history. So these might be people browsing, and maybe people clicking at some in some place. And somehow I want to learn the joint or some conditional of one of those given the others, whatever. But for the purpose of this discussion, let's say we just want to learn the joint. So we've got the joint distribution between these three things and the joint distribution between these three things, and they're just different tables. There are different joint occurrences of these three things together that are unrelated to the joint occurrence of these three things. So we could learn a separate models for each of them, or we could say, well, whatever the contexts in which we talk about a URL, it has some meaning that should be the same whether it's when somebody clicks on that URL or when I look at the sequence of words that are in that page. So what I could do is learn a representation for URL that's shared between these two tasks. So that's the idea, right? We define representations that are going to be learned, and we say that these representations for the same object but in different contexts and different tasks should be the same. And we tie those parameters together, and we can train simultaneously for these two tasks by just whatever method we like, but under the constraint that the parameters of this red box should be the same as the parameters of that red box. And we've applied these kinds of things to mixing data from different sources like WordNet, Freebase, ImageNet, and so on. So the way I think about AI, how it's going to come about, you can think of it maybe search engine becoming really, really, really smart. That AI is going to need all the sources of data we have, and those sources of data are not uniform. They're not, they don't come in one nice table with inputs and targets. There are all a bunch of different types of tables like this, but many of these will have words. Many of these will have people names. Many of these will have images, videos, and these objects can be represented always in a consistent way across all these tasks. And that allows to generalize very quickly to tasks for which you have very little data, just as I said earlier. Okay. There's another notion that's connected to representation, and it's the notion of invariance. I mentioned it at the beginning of my presentation, and disentangling that I also mentioned quickly. So what is it about invariance? So as I said, when you design features by hand, you try to design those features for a particular task so that they would be insensitive to the factors that don't matter. If you're doing speech recognition, you'd like to have features that don't vary when you change the microphone, when it's a different person speaking. You'd like to have speaker-independent features. However, if you're doing speaker identification, you're trying to figure out who's speaking, well, you want to throw information about which phonemes were pronounced. So depending on the task, there are things you want to throw away and things you want to keep. But what if you're doing unsupervised learning? If you don't know what the task will be. And when I think about AI, I think about a machine that collects information about the world and tries to figure out all of the factors that explain everything that is observed, just like scientists do. Then, if you're the engineer that has to build a bridge, you've got a particular task, and you can ignore, most of the science and just keep the part that, matters for you. But the first step is the science, is the understanding part. And here, we don't have to choose what to throw away. We just need to separate out the speaker information and the phonetic information so that when later you want to do something with it, it's going to be easy. So that's what disentangling is about. The funny thing with this notion, well, you might believe and you might be right that there's no hope of doing it unless you tell the machine, here's an example of speaker identity and here's an example of the phoneme. And maybe you're right, but I have the hope and the intuition, a strong intuition that we can do a lot of mileage just because of the statistical structure that's present in the data. So in the 20 examples I showed where there was a simple manifold structure of classes, the manifold structure, you don't need someone to tell you about the classes. You don't need someone to tell you about the invariances. They are there. They're just striking. They just come out of you. And any reasonable machine learning should be able to disentangle the class information from the variation within the class because it's so obvious. And so actually there are a couple of papers suggesting that methods that seem to be completely general and don't have anything in particular for disentangling apparently actually do a little bit of disentangling in the sense that if you look at the features that have been learned at different levels, you find features as you go higher up that are more sensitive to some factors that are known a priori and less sensitive to others. So something is going on that we don't fully understand. I'll come back on this question at the end of my presentation tomorrow, hopefully. But in both of these examples, there was something particular, which is a notion you find in many deep learning papers, which is sparsity of representation. So what does it mean, sparse representation? So in those two examples, actually, it was trained with some kind of sparse autoencoder. I'll come back to order encoders later, but basically it's a way to learn representations. And a sparse representation is simply one in which most of the entries are 0 or some other constant you can choose. Actually, the fact that it's 0 doesn't matter. What matters is that the derivative, as I move the input, is 0. So I have some attributes that will remain in a state corresponding to basically not applicable. So practically, what we do is we impose a penalty on the representation, like an L1 penalty, that's going to make many of the bits or many of the numbers there close to this special value like 0. But really, it makes sense only because the way we get those zeros means that if we make a small change in the input, that's going to stay 0. What's nice about sparse representations is that it also helps us deal with another concern that has been raised for decades against neural nets, which is, well, we have these fixed size vectors that are supposed to represent complicated objects. And really, in computer science, typically the way we deal with things is we have variable-sized data structures. So how do we get around that? We can ask the same question about the brain. I mean, the brain, okay, it has a huge representation, but it's a fixed size one. So how does it handle things that naturally have a variable size? Well, if you use sparsity, then you get a variable size representation in a sense within a fixed size one. So if most of the bits are going to be 0, then by changing how many bits are on, it's like changing the size of the data structure. Of course, there's a limit to how big an object you can represent. And we probably have limits like that in our brain as well. There's another hint that we can give to our models, and that has been used in the literature to help learn good representations, and it's the temporal or spatial coherence and temporal or spatial scales. Actually, we talked earlier about multiple time scales or spatial scales. That makes sense because there is temporal or spatial coherence, predictability. So right now in this room, there are a number of things that don't change. Even though I keep speaking and I move around, the identity of the persons in the room doesn't change. The room itself remains where it is. So each frame coming to my brain has a lot in common with the previous one. And that's the kind of prior that's been exploited in many learning algorithms. And it's easy to impose that kind of prior if you work with representations that are learned. You're basically saying, I want my representation to have the property that the vector at t and the vector at t plus 1 should be close to each other. And there are many ways you can represent that. And for space, it's the same thing. One thing that's interesting in terms of disentangling is that actually, if you think about it, there are things that change slowly and things that change quick. And these factors are different. So here's a hint for separating out factors. Right? The things that are constant about the scene here are very abstract notions, categories. But there are things that change quickly, like I'm actually moving all the time, and my position is something that changes fairly quickly in comparison. So there are different factors at play that have different timescales. Okay, so I guess only 10 minutes left, and that was my introduction. So the second part, which I will continue after the break, is going through some of these algorithms for learning representations. I'm going to start with the baby steps. Good old neural nets from the late 80s, or multi-layer networks, whatever you want to call them. So I'm sure all of you know what logistic regression is, but I'm not sure all of you know what a neural net is. So I'm going to explain neural nets in terms of logistic regression. So let's say you wanted to do logistic regression, but what you're going to do is you're going to imagine you have different variables you want to predict from your input. And these would be, and you could, if you knew what these variables should be, then you could simply do a logistic regression to train, each of these as a, say, sigmoid of linear combination of the inputs. And once you've trained these ones, you could train another logistic regression on top that would predict the thing you care about. And the idea of neural nets is we can do this without having to specify what the intermediate variables here should be. We can let the learning algorithm discover what they should be. And we can do that by simply optimizing the parameters here and here together so as to make the error we make here as small as possible. So that's the basic idea. And of course, you can have more layers. And how are we going to train all of these together? We're going to use something called backprop. So the word backprop has been used incorrectly many times in the literature. So let me get it straight. Backprop is not a learning algorithm. It's a procedure for computing gradients. That's it. Then once you've got the gradients, you can use the gradients in many different ways. And the most common way is gradient descent or stochastic gradient descent. But you could use it as part of other gradient-based optimization methods like conjugate gradients or LBFGS. And the way we're going to compute those gradients is important because you could easily get it wrong, not just in the sense of getting the wrong answer, but getting it very inefficiently. To get those, and actually it's almost something magical how you can compute those derivatives. Because if nobody told you how to do it, you might resort to things like difference methods in order to estimate derivatives, and that would be very, very inefficient in comparison to backprop. So backprop is a super efficient way of estimating gradients or derivatives. All right, and it relies on the chain rule. So what is the chain rule? It arises out of the composition of function, which is exactly what we're into here. So we've got a function, z is f of y, but y is g of x. And so the chain rule tells us that dz dx is dz dy times dy dx. And why is that true? Well, let's do a little graphical thing. So we've got x that influences y and y that influences z. dy dx tells us what happens to y if I make a very small change in x and vice versa. You can see that what you want with dz dx is, what happens to z if I make a small change of y is it's going to make a small change of, what happens to z if I make a small change in x? The small change in x is going to create a small change in y, and I'm going to get that by multiplying delta x by dy dx. And then, actually, here's the equation. Small change in x is going to be translated into a small change in y by multiplying delta x by dy dx. And then the delta y gets multiplied by dz dy in order to give me the delta z. Right? So this is what these derivatives mean. And now, because that change, those changes get multiplied, the delta z is just dz dy dx times delta x, and you can get that just algebraically by plugging this definition into this, and you get the result. Okay. And what if you had two ways that x could influence z? Well, you would simply add the way in which x could influence z through the first path with the way it could influence it through the second path, and you get this form of the chain rule. And in general, if you had more ways, then you would sum over all the paths, and for each path you would multiply along the path. And if you had something more complicated like a graph, an arbitrary graph of dependencies of functions variables that depend on each other. So this is not like a graphical model. This is just what they call a flow graph, where you put down your computation as composition of simple things. For any node x in the graph, you want to know how it influences some final node z, actually any node further down. You can write it down through this completely general rule that says I'm going to look at the descendants of x, let's call them y1 to yn, or successors of x. And if somebody gives me dz, dyi for each of these guys, I can multiply them by dyi dx and sum them, and I get dz dx. And so this gives me a recursive formula for computing derivatives through any graph that performs some computation. And any program that computes can be written down as a graph like this. And this is how automatic differentiation is implemented. It sees the program as just composition of simple operations. And for each of those operations, it knows how to get the derivative of the operation, like how x influences yi, which is this arc. And for each of the possible types of operation, it knows how to compute these things. And it's going to maintain a state of these derivatives with respect to each node and recursively compute them from top to bottom. This is actually what the next picture does. So in the neural net, you've got graphs like this. For example, you compute the negative log likelihood minus log p of y given x as the minus log of one of the units which corresponds to the right answer. And then you can apply this recipe to compute derivatives with respect to the output units, and then propagate that into hidden units and parameters. And you can do that more generally, and this is a general sort of backprop in any kind of flow graph, not just neural nets. It has two phases, one in which we compute outputs, actually a single node which would be your loss, the thing you want to minimize. So that's the fprop phase. And the backprop will go exactly in the opposite direction from the final node, go and visit in the inverse order, and at each node apply the same rule that I explained, where each node gets to have a derivative. So in addition to x, for each node x, we're going to have a dz dx, and we're going to compute it by using the dz dy that we've already computed for the successor nodes upstream, downstream, sorry. And so we go in the same order backwards. We compute these dz's, dx, and some of these will be parameters, and we can use that for computing gradients. Is there any question on this? This very general algorithm. Everybody is comfortable with this? You should be able to, take any set of equations that computes a loss given some parameters and apply this recipe blindfolded. That's what I tell my students when I give them an exam. So, all right. Once you understand this principle, you can see how you can compute gradients in structures that are more complicated than just a normal feed-forward neural net. So for example, the recurrent net that I had mentioned a little bit briefly earlier has this kind of graph where we've got inputs and we've got states, and the state at time t is obtained by some function of the state at time t minus 1 and the input at time t, and so on. So now the graph has this shape which we called unfolding in time. But we can apply the same recipe. We just apply this general recipe, and now how is it going to proceed? You're going to compute all of these states. You're going to compute some loss, which depends on the states at some point, and compute derivatives backwards in time in order to compute gradients with respect to the states and to the parameters. Actually, the graph doesn't have to be a chain like this. It could be a tree. And this is how some of the parsing methods and other recursive networks. Recurrent usually is like this, and recursive means we build a kind of tree of operations. And the operations themselves don't have to be things like sigmoid and sums and products. It could be any kind of computation for which you can compute derivatives. For example, it could involve some max, like you have a bunch of things and you take the max and you output the max. So this is differentiable almost everywhere, and more importantly, it's continuous. And because of the continuity, this is really important. You can train such things with stochastic gradient descent, no problem. And we'll see some examples of that. Finally, actually applying this recipe by hand is quite feasible, but you can easily make mistakes. Because we're not machines. Actually, we are machines, but not that kind of machine. And so if you can, it's much better to use automatic differentiation. Basically, the idea with automatic differentiation is the programmer specifies the graph that computes outputs and costs, given inputs and parameters. And a completely dumb algorithm does automatic differentiation and will compute gradients for you and will not make any mistake. And it's very easy to debug these things because you can debug for each type of computation you do here, like adding, multiplying, taking an exponential, whatever. You can debug each of these separately. And once they're debugged, you can compose them and it works. And you can also check that the composition works. So Theano is an automatic differentiation compiler that my students have written, and that's in Python, and takes Python expressions that are similar to NumPy expression, which is sort of the MATLAB environment like for Python, and generates code that will efficiently do this and this in C or GPU. But the important thing is it does this, which makes life much easier and less error prone. So back to deep supervised neural nets. A few slides earlier, I said that until 2006, we didn't know how to train them. But now, thanks to better initialization and use of nonlinearities like rectifiers and maxout and dropout, we are able to train networks with 5, 6, 7, 8, 9 layers, something we didn't know how to do before. And somehow these generalize a lot better than the old neural nets of the 80s and 90s, which had only one or at most 2 hidden layers. Okay, so I'm going to stop here for the break.